Good morning. Today we will discuss about the proton magnetic resonance spectroscopy. Before starting this, we will discuss about the difference in between chemical method and spectroscopic method. Actually, here this PMR is used for the structural determination, and structural determination is important in industry as well as in research field, because here we find out we assign or deduce the structure of novel compound as well as which compound are synthesized in the laboratory. Means the structural determination is the main theme or main point or main target of that particular researcher as well as chemist. So here for the structural determination there are two methods: chemical method and spectroscopic method. Actually, spectroscopic method is under the heading physical method. Now here there are some difference in chemical method and spectroscopic method. One major difference is that this chemical method required more sample, and in the spectroscopic method we required less sample. Now when we consider the chemical method, there are organic qualitative analysis, and for the organic qualitative analysis we required a lot of sample as well as a lot of reagents as compared to spectroscopic method. Now when we consider the spectroscopic method, for the PMR we required only 5 milligram sample. And another thing is that in case of chemical method, sample is recovered. Sample is not recovered. Sample is not recovered. But in spectroscopic method, sample is recovered. This is the another difference. Third difference is that suppose you consider the organic qualitative analysis regarding the chemical method, it required lot of time. More time is required here, but in case of spectroscopic method, less time is required. Less time is required. Means this method is time consuming method. Time consuming method, but in this case time required very less. Then next one, in spectroscopic method, accurate structural determination is obtained. Accurate structure is obtained, but in case of chemical method, those organic compounds in the library or in the practical book, only those compounds are possible structural determination. Means here some limitations to structural determination. Structural determination means when we compare in between spectroscopic method and chemical method, here this having the more advanced as well as more developed method as compared to chemical method, but still having this spectroscopic method having some limitations. These limitations are costly equipments, as well as operator is required. But when you overcome these 2 points, instrument as well as operator required, this spectroscopic method is more predominant or more useful as compared to chemical method. And here one more point related to this spectroscopic method is interpretation of spectra. Interpretation of spectra. And more trained and those person are interpret the spectra, you must know regarding the spectroscopic method, their principle as well as another things related to spectroscopy. Now in case of spectroscopy, there are so many spectroscopic methods like UV as well as IR, NMR, then mass. These are the some spectroscopic methods. The name of these spectroscopic method are related to their electromagnetic radiation is used. When we consider the UV spectroscopy, here ultraviolet rays are used. In case of IR, there are infrared rays are used. In case of NMR, there are radiations are used. But in case of mass, there are no any particular radiations are used. But still, it is useful for the structural determination, and hence it is under the heading spectroscopic methods. Now here, when we consider the UV spectroscopy is used to know the dying and immune system. At the same time, this IR gives the idea about different functional group. And among these all, NMR is move towards the clear-cut idea to find the structure, and it is related to proton as well as 13C. And mass spectroscopy is related to the fragmentation and M/Z value. So we will see the 1H NMR. Actually, when we see the principle of this 1H NMR, or in another name of this spectroscopy is proton magnetic resonance spectroscopy, because this spectroscopy is related to H1. Actually, this proton having 3 isotopes, H1, deuterium and tritium. Among these, this is proton NMR active that is I equals to 1 half, here 1, but this tritium is NMR inactive. Tritium is NMR inactive. Now here we will see some properties of this proton, that is natural abundance, natural abundance of this H1 is 99.98%, and the sensitivity is 1, means as compared to 13C, here natural abundance is 1.11%, here sensitivity is very less, then absorption frequency in megahertz, it is 100 and it is 25, means it is 1/4 less as compared to H1. Okay, this is another part. Actually it is under the heading CMR and this is PMR. Now we move towards the principle of this NMR. We move towards the principle of this NMR. Now in this case, the nucleus of the proton is considered as a magnet and it having the spinning, means this is spin bar magnet. Now here, when external magnetic field is applied, suppose this is H0 and radio frequency is applied, and suppose this is D0, and hence there are, suppose this is clockwise spinning, okay, and frequency of this spinning bar magnet of this nucleus is matched with the frequency of radio electromagnetic radiation. It change their spin to anti-clockwise, and at the same time there are signal is appear, and this signal is recorded in the form of graph. This is called as NMR spectrum. This is called as NMR spectrum. Means what happens in this case? There are spin state change. There are spin state change. This is the basic principle of PMR. Means what happens in this case? The proton, when there are external magnetic field is applied, at the same time there are radio waves are applied on this, the spin state, means this alpha spin is changed to beta spin. This is the basic principle of NMR, means alpha spin state changed to beta spin, and at the same time there are signal is appeared in the form of graph. This is called as NMR spectrum. Now we will see some examples related to this. you know very well about this. This proton having the nucleus and electron are revolving around this nucleus. This is positively charged and this is negatively charged. And you know very well about this. This proton is not only attached to hydrogen, but it attached to chlorine, it attached to oxygen, it attached to carbon, it attached to nitrogen. And hence this electronegative electrons, this electronegativity is somewhat moved towards this chlorine or oxygen or nitrogen, and hence this shield, actually these electrons are around this nucleus, is considered as a shield, or it is the envelope. It is the envelope around this nucleus, and when we apply the external magnetic field, this external magnetic field first interacted with this envelope of these electrons, and hence this nucleus become a shielded. This nucleus become a shielded. But when this proton is attached to electronegative element, due to the minus I effect, this shield is somewhat moved towards the chlorine or oxygen. Suppose you consider here, suppose this proton is attached to oxygen, then here this is moved towards the oxygen, and the envelope around this nucleus is somewhat moved towards the oxygen or moved towards the electronegative element, and this is called as deshielding. This is called as deshielding. Means shielding and deshielding is depending upon the which group or which proton is attached to hydrogen. Now means when we see the spectra here, this is TMS, this is a TMS, and here this side is shielded region. This side is shielded region. Means here this is shielded region and this is deshielded region. TMS 0 and the scale is up to 20. Means here those protons are shielded, are appeared here, the signal is appeared in this region, and when there are deshielding group or any particular electronegative group is attached to that proton, then this signal is moved towards the deshielded region or towards the del value 20. Now we will see some examples. Types of proton. Types of proton is nothing but the number of signals appear in the spectrum. Now there are so many examples. Suppose you consider Here CH3 and CH3 means ethane. In this compound there are total 6 hydrogens, and these 6 hydrogens having the same chemical environment, same chemical environment and hence such type of compound having the only one signal in the NMR spectrum means one type of proton equals to the one signal. Now we will see some another examples. Now we take another example, chloroethane. Here these 3 proton having the same chemical environment, and hence we consider as they having the same signal, and it is noted by A. And CH2 means these 2 proton having the same chemical environment, and this is B. So in this case, this compound, suppose you consider the spectra, this is TMS at 0, tetramethylsilyl. Here we already discussed this CH2 is attached to chlorine, and hence it is more deshielded, and this CH3 is away from Cl, means this is less deshielded is nothing but it is shielded, and this is deshielded, and hence it gives a signal, means this signal for CH3 because this is shielded or less deshielded, and this signal for CH2 means on the basis of types of proton, this compound shows the 2 signals in the PMR spectrum. Now we will see some another examples here. CH3, CH2, and here CH3. Now in this case, here clear cut idea about the different chemical environment of this CH2, and hence this appear as a B and this is appear as a A, different 2 signals. But in this case, this CH3 and this CH3 having the same chemical environment, and here these 6 protons having the one signal, and this middle one is having the another signal, means such compound having the 2 signals. Now we will see one more examples here. Now when we compare in between these 2 compounds, there are one more oxygen is in between CH2 and CH3, and due to the introduction or insert the oxygen in between CH2 and CH3, these having different chemical environment, so this compound having the 3 signals A, B and C. So there are 3 signals. Now we will see some more examples. Okay, it is okay. Now we will see the spin coupling. spin coupling, spin coupling, or it is called as splitting. It is called as splitting. For this we take one example, chloroethane. This is A and this is B, and this is TMS at 0, it's CS3, this is CH2. Actually it is at 60 megahertz. Now we increase the radio frequency here, external magnetic field up to the 300 megahertz, and such spectra is appeared look like this. This is TMS. Suppose it appeared at 1.1 Dale value, and suppose it appeared at 2.1. Now this CS3 group is splitted on the basis of n+1 formula. On the basis of n+1 formula. Now here, when you apply the n+1 formula for the CS3, n is the neighboring proton, 2 plus 1 means it gives 3 lines. 3 lines is nothing but the triplet, and this spectra is look like this. Signal is split into 3 lines, and this is called as triplet. This is called as triplet. Now here this CH2, when we apply the n+1 formula, here 3 plus 1, it gives 4 lines, nothing but the quartet, and quartet it look like this is CH2, and this split into 4 lines. This is nothing but the quartet. The chemical shift value is doesn't change here. This is 1.1 and this is 2.1 Dale value in ppm. Dale value in ppm. This is called as spin coupling. Means n is nothing but the neighboring protons, and the formula is n+1. Okay, so I will stop here. Thank you.